The year is 2157. Dr. Elena Vasquez stands alone in the observation deck of humanity's most distant outpost, a research station orbiting Proxima Centauri. Through the reinforced viewport, she gazes at a sight that would have been impossible for her ancestors to imagine, a universe noticeably dimmer than the one they knew. The familiar constellations of Earth's night sky are no longer visible from this distance, but more troubling still. Even the brightest galaxies appear fainter than the historical records suggest they should be. She checks her instruments again, hoping for an error, but the data is undeniable. The universe is not just expanding. It's accelerating away from itself so rapidly that entire clusters of galaxies are disappearing beyond the cosmic horizon, their light stretched into invisibility by the relentless expansion of spacetime itself. This moment, fictional though it may be, represents a very real possibility that cosmologists have been grappling with for decades. Are we living in a universe that is slowly but inexorably fading away? Could future generations of intelligent beings, whether human or otherwise, find themselves in a cosmos so diluted and expanded that the very stars become unreachable, their light too redshifted to provide warmth or energy? The question haunts our understanding of cosmic evolution. Will we be among the last civilizations to witness the universe in its full glory? To understand this cosmic twilight, we must first journey back to the very beginning, to a time when the universe was nothing but a seething cauldron of energy and possibility. 13.8 billion years ago, in the first moments after the Big Bang, the cosmos was unimaginably hot and dense. There were no stars, no galaxies, no planets, just a smooth soup of fundamental particles and radiation expanding and cooling as spacetime itself stretched outward in all directions. For nearly 400,000 years, the universe remained opaque, shrouded in a fog of ionized plasma that scattered light in every direction. But then, as temperatures dropped below a critical threshold, something magnificent happened. Electrons began to combine with protons to form the first neutral hydrogen atoms, and suddenly, the cosmic fog cleared. Light could travel freely through space for the first time, and the universe became transparent. This moment, known as recombination, marks the birth of the cosmic microwave background, the afterglow of creation itself, which we can still detect today as a faint whisper of radiation permeating every corner of the sky. But even as the universe became transparent, it remained dark. There were no sources of light, no stars to illuminate the cosmic void. This period, aptly named the Dark Ages, stretched on for hundreds of millions of years. During this time, gravity was the only force at work on cosmic scales, slowly pulling together the tiny density fluctuations left over from the Big Bang. Like a conductor orchestrating a vast symphony, gravity gathered the scattered hydrogen and helium into ever larger clumps, setting the stage for the most transformative event in cosmic history. The first stars were nothing like the ones we see today. Born from pristine clouds of primordial gas, they were massive beyond imagination, perhaps 100 or even 200 times more massive than our sun. These stellar giants burned through their nuclear fuel with reckless abandon, shining with the brilliance of millions of modern stars. But their glory was brief. Within just a few million years, they exhausted their fuel and collapsed catastrophically, exploding as supernovae that lit up the early universe like cosmic fireworks. These explosions did more than just provide a spectacular light show. They forged and scattered the first heavy elements: carbon, oxygen, silicon, iron, the building blocks of planets and life itself. The pristine universe of hydrogen and helium was forever changed, enriched with the ashes of stellar death. This cosmic alchemy, the transformation of simple elements into complex ones within the nuclear furnaces of massive stars, represents one of the universe's most profound acts of creation through destruction. As we fast forward through cosmic time, we witness the gradual construction of the cosmic web, a vast network of dark matter filaments that stretches across billions of light years. Along these filaments, like cities built along ancient trade routes, the first galaxies began to form. These early galactic metropolises were violent, chaotic places, constantly merging and colliding as gravity pulled them together. At their centers, supermassive black holes grew fat on infalling gas and stars, powering brilliant quasars that could be seen across the observable universe. The era of quasars represents perhaps the most energetic period in cosmic history. These ancient beacons, powered by black holes millions of times more massive than our Sun, outshone entire galaxies. They were the lighthouses of the early universe, visible across billions of light-years of space and time. Yet today, as we scan the modern cosmos with our most powerful telescopes, we find that bright quasars have all but vanished. The universe has grown too old, too settled, for such violent displays of energy. The supermassive black holes that once powered these cosmic lighthouses have consumed most of their available fuel, settling into a quiet dormancy that speaks to the universe's advancing age. Dr. Martin Schmidt stands in the dome of the Palomar Observatory on a crisp California night in 1963. He has been staring at photographic plates for hours, trying to decipher the strange spectral lines of a peculiar star-like object designated 3C273. The lines don't match any known element, and Schmidt is beginning to wonder if his instruments are malfunctioning. Then, in a moment of inspiration that will revolutionize our understanding of the cosmos, he realizes that the lines do belong to hydrogen, but they are shifted so far toward the red end of the spectrum that they are almost unrecognizable. The implications hit him like a thunderbolt. This object is not a nearby star at all, but something unimaginably distant and powerful, receding from us at tremendous speed. He has just discovered the first quasar, opening a window into the violent infancy of the universe. Schmidt's discovery was more than just an astronomical breakthrough. It was a revelation about the nature of cosmic time itself. The light from 3C273 had been traveling through space for billions of years before reaching Earth, meaning that Schmidt was not just looking at a distant object, but peering back through time itself. This concept of look-back time has become one of astronomy's most powerful tools, allowing us to study the universe at different epochs simply by looking farther away. As our telescopes became more powerful and our understanding deepened, we began to map the history of star formation across cosmic time. What we discovered was both beautiful and melancholic. The universe had already passed its prime. The peak of star formation occurred when the cosmos was just 3 billion years old, less than a quarter of its current age. Since then, the rate at which new stars are born has been steadily declining. We are living not in the spring or summer of the universe, but in its autumn, watching as the great stellar furnaces slowly burn out one by one. This cosmic aging is not uniform across all regions of space. In the dense cores of galaxy clusters, star formation ceased long ago, leaving behind populations of ancient red stars slowly fading away. But in the spiral arms of galaxies like our own Milky Way, star formation continues, albeit at a much reduced pace compared to the universe's youth. These stellar nurseries, illuminated by the blue glow of young, massive stars, represent islands of continued creation in an increasingly quiet cosmos. The story of cosmic evolution is also the story of structure formation, the gradual assembly of matter into ever larger and more complex arrangements. From the initial tiny fluctuations in the early universe emerged the first stars, then the first galaxies, then groups and clusters of galaxies, and finally the vast superclusters and filaments that make up the cosmic web. Each level of this hierarchy tells us something about the forces that have shaped our universe over billions of years. But perhaps the most profound discovery of modern cosmology is that this hierarchy will not continue to grow indefinitely. In 1998, two independent teams of astronomers studying distant supernovae made a shocking discovery that would overturn our understanding of the universe's fate. They found that the expansion of the universe, rather than slowing down under the influence of gravity as everyone expected, was actually accelerating. Some mysterious force, which we now call dark energy, was pushing galaxies apart at an ever-increasing rate. The implications of dark energy for the future of the universe are both fascinating and deeply unsettling. As the acceleration continues, the cosmic web will begin to dissolve. Galaxy clusters will be torn apart as their constituent galaxies recede beyond each other's gravitational reach. Eventually, even individual galaxies will find themselves alone in an increasingly empty universe, their nearest neighbors receding faster than the speed of light, effectively disappearing beyond the cosmic horizon. Dr. Sarah Chen peers through the eyepiece of the newly commissioned extremely large telescope, its 40-meter mirror gathering photons that have traveled billions of years to reach Earth. She is part of an international team studying the most distant galaxies ever observed, their light stretched and reddened by the expansion of space itself. What she sees troubles her deeply. These ancient galaxies appear to be moving away from us at nearly the speed of light. Soon, within a few billion years, their light will be stretched beyond the capabilities of any conceivable telescope to detect. Future astronomers, no matter how advanced their technology, will look out into space and see nothing. They will inhabit island universes, isolated and alone in an ever-expanding cosmic ocean. This scenario, known as the Big Rip or the heat death of the universe, depending on the exact nature of dark energy, represents one possible future for our cosmos. In this future, the last stars will burn out roughly 100 trillion years from now, leaving behind a universe populated only by black holes slowly evaporating through Hawking radiation. Eventually, even the largest black holes will disappear, leaving nothing but a thin soup of elementary particles expanding into an increasingly cold and empty void. But before we despair at this cosmic fate, we must remember that we are privileged to live during what may be the most interesting epoch in the universe's entire history. We exist at a time when stars still shine brightly in the night sky, when galaxies cluster together in magnificent cosmic cities, when the cosmic microwave background is still detectable as a whisper from the Big Bang itself. We are the first generation of humans to understand our place in this vast cosmic story, and possibly among the last who will be able to see the universe in all its glory. The James Webb Space Telescope, humanity's most ambitious space observatory, floats silently in the darkness beyond Earth's orbit, its golden mirrors perfectly aligned to capture the faintest glimmers of light from the most distant corners of the universe. As it peers deeper into space and further back in time than any telescope before it, JWST is revealing the universe's infancy in unprecedented detail. We can now see galaxies as they appeared when the cosmos was just 400 million years old, during the epoch when the first stars were igniting and beginning to clear the fog of neutral hydrogen that had shrouded the universe since recombination. What JWST has shown us is both wonderful and sobering. The early universe was a more vibrant, more active place than our current cosmic epoch. Galaxies formed and merged at a breakneck pace, their central black holes growing rapidly as they devoured surrounding gas and stars. Star formation rates were orders of magnitude higher than what we observe today. In essence, the universe was younger, more energetic, more alive. We are seeing the cosmos in its prime, and by comparison, our current universe appears almost sedate. This observation leads us to a profound realization. We may indeed be among the last civilizations to witness the universe at anything approaching its full potential. Future beings, whether they evolve naturally or represent our own distant descendants, will inhabit a cosmos that is progressively darker, emptier, and more isolated. The rich tapestry of cosmic structure that we can observe today, the spiral arms of galaxies, the intricate patterns of stellar nurseries, the violent dance of interacting galaxies, will gradually fade into memory. Yet there is beauty in this cosmic transience. The very fact that we exist at all represents a remarkable convergence of circumstances. The universe had to be old enough for heavy elements to have been forged in the cores of massive stars and dispersed by supernovae, but young enough that stars were still forming at a reasonable rate. The expansion had to be fast enough to prevent the early collapse of the cosmos, but slow enough to allow structure formation. The strength of the fundamental forces had to be precisely calibrated to allow the existence of stable atoms, molecules, and ultimately, life itself. In contemplating our cosmic context, we might draw parallels to autumn on Earth. Just as the changing seasons bring a particular kind of beauty, the golden light of shorter days, the spectacular colors of dying leaves, the poignant awareness of time's passage, so too does our cosmic autumn have its own unique splendor. We live during the era when the universe has reached a kind of maturity, when the violent chaos of its youth has settled into more stable patterns. when complexity has had time to emerge and evolve. The story of cosmic evolution is also the story of increasing complexity emerging from simplicity. From the uniform smoothness of the early universe arose the rich structure we see today. Stars with their intricate nuclear fusion processes, planets with their complex geological cycles, and ultimately life itself with its remarkable ability to organize matter into ever more sophisticated forms. Each level of complexity builds upon the last, creating a hierarchy of organization that spans from quarks to quasars. But complexity requires energy, and energy requires fuel. The stars that light our skies are slowly but steadily converting hydrogen into helium, helium into carbon, carbon into heavier elements, working their way up the periodic table until they reach iron, the ash heap of nuclear fusion. At this point, fusion can no longer provide energy, and the star faces a crisis. Depending on its mass, it may shed its outer layers to become a white dwarf, collapse to form a neutron star, or explode as a supernova and leave behind a black hole. Each of these stellar endpoints tells us something about the ultimate fate of complexity in the universe. White dwarfs will continue to radiate heat into space for trillions of years, gradually cooling from white-hot to red to brown to black. Neutron stars, those incredibly dense remnants of stellar collapse, will slowly spin down as they lose energy to their magnetic fields and gravitational waves. Black holes, perhaps surprisingly, will prove to be the longest-lived objects in the universe, but even they are not eternal. Through the quantum process discovered by Stephen Hawking, they will slowly evaporate, returning their mass to the universe as radiation. Dr. Hawking himself, confined to a wheelchair but with a mind that roamed freely through the cosmos, gave us one of the most profound insights into the nature of black holes and the ultimate fate of information in the universe. His discovery that black holes emit radiation challenged our understanding of thermodynamics and information theory, leading to paradoxes that physicists are still working to resolve. The image of Hawking, unable to speak without the aid of a computer, nevertheless unlocking some of the deepest secrets of the cosmos, serves as a powerful reminder that the universe's greatest mysteries often yield to human ingenuity and determination, regardless of physical limitations. As we trace the future evolution of the cosmos, we encounter scenarios that challenge our imagination. In the far future, when all the hydrogen has been fused into heavier elements and star formation has ceased, the universe will enter what cosmologists call the degenerate era. During this unimaginably long period, lasting perhaps 10 to the power of 40 years, the only sources of energy will be the slow decay of massive objects and the occasional collision of stellar remnants. Planets will slowly spiral into their parent stars due to gravitational wave radiation. Stellar remnants will settle to the centers of galaxies, eventually coalescing into massive black holes. But even this is not the end. In the black hole era, lasting until 10 to the power of 100 years after the Big Bang, these massive black holes will slowly evaporate through Hawking radiation, returning their energy to an increasingly dilute cosmos. The larger the black hole, the longer it takes to evaporate, so the supermassive black holes at the centers of galaxies will be among the last objects to disappear from the universe. Finally, in the aptly named dark era, the universe will consist of nothing but elementary particles, electrons, positrons, neutrinos, and photons, expanding into an ever larger, ever colder space. Even then, quantum mechanics suggests that random fluctuations might occasionally create temporary structures, perhaps even brief moments of complexity arising from the quantum vacuum itself. But these will be rare events, separated by inconceivable gulfs of time and space. This cosmic timeline raises profound questions about the meaning and purpose of existence. If the universe is destined for such a bleak future, what is the significance of our current moment? What meaning can we find in our brief flickering of consciousness against the backdrop of cosmic eternity? Perhaps the answer lies not in the duration of our existence, but in its depth and richness. We are the universe's way of knowing itself, the products of billions of years of cosmic evolution that have led to the emergence of consciousness and intelligence. Through our eyes, the cosmos contemplates its own beauty and mystery. Through our minds, it comes to understand its own structure and history. In a very real sense, we are the universe becoming aware of itself. The great astrophysicist Carl Sagan once said that we are made of star stuff, and this is literally true. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of these elements were forged in the nuclear furnaces of ancient stars and dispersed by supernovae billions of years ago. We are not separate from the universe. We are part of it, intimately connected to its history and evolution. This connection suggests that our responsibility as conscious beings extends beyond our own immediate concerns to encompass the cosmos itself. We are the current custodians of cosmic awareness, the temporary vessels through which the universe experiences wonder, beauty, and understanding. This is both a tremendous privilege and a profound responsibility. As we develop more powerful telescopes and more sophisticated theories, we are pushing back the frontiers of cosmic ignorance. Projects like the Event Horizon Telescope, which gave us our first direct image of a black hole's shadow, represent humanity at its best, using our collective intelligence and technological prowess to answer fundamental questions about the nature of reality itself. When we saw that first image of the supermassive black hole at the center of Galaxy M87, we were not just observing a distant object. We were witnessing the confirmation of Einstein's general relativity in the most extreme gravitational environment in the universe. Similarly, the detection of gravitational waves by LIGO and Virgo has opened an entirely new window on the cosmos. These ripples in spacetime itself, caused by the collision of black holes and neutron stars billions of years ago, allow us to study the universe in a completely new way. We are no longer limited to the electromagnetic spectrum. We can now listen to the universe itself, hearing the whispers of cosmic cataclysms that occurred when the universe was much younger. Each of these discoveries adds another piece to the cosmic puzzle, helping us understand our place in the grand scheme of things. We are learning that the universe is far stranger and more wonderful than our ancestors ever imagined. Dark matter outweighs ordinary matter by 5 to 1, yet we still don't know what it is. Dark energy, which makes up nearly 70% of the universe, remains equally mysterious. We live in a cosmos where the majority of everything is composed of substances we cannot see, touch, or directly detect. Yet despite these mysteries, or perhaps because of them, we continue to push forward, driven by an insatiable curiosity about the nature of existence. This curiosity is one of humanity's greatest gifts to the universe. Through our questions and investigations, we give meaning to cosmic evolution, transforming what might otherwise be a meaningless sequence of physical processes into a story of growing complexity and understanding. The question of whether we will be the last to see the stars is ultimately a question about the future of consciousness in the universe. Will intelligence and awareness continue to exist in some form even as the cosmos grows dark and cold? Will our distant descendants, whether biological or artificial, find ways to survive the death of the last star and the evaporation of the last black hole? These questions may be unanswerable with our current knowledge, but they remind us that our cosmic story is far from over. Even if biological life cannot survive the far future of the universe, the information and understanding we create today might persist in some form. Our knowledge of cosmic evolution, encoded in our books and computers and cultural traditions, represents a kind of cosmic memory, the universe's attempt to preserve its own history and self-understanding for posterity. In the end, whether we are truly the last to see the stars may matter less than the fact that we are here now, able to appreciate their beauty and understand their significance. We exist during a remarkable epoch when the cosmos is old enough to have developed complexity and consciousness, yet young enough that the night sky still blazes with the light of countless suns. We can see the cosmic microwave background, hear the whispers of gravitational waves, and peer back through time to witness the birth of the first galaxies. As we stand on our small planet orbiting an ordinary star in an unremarkable galaxy, we might feel insignificant against the vastness of space and time. But we are the products of that vastness, shaped by cosmic forces over billions of years. We carry within us the history of the universe itself, from the Big Bang through the formation of the first elements, the birth and death of countless generations of stars, the slow assembly of the cosmic web, and the gradual emergence of complexity and consciousness. We may indeed be among the last civilizations to witness the universe in its current glory. Future beings might inherit a cosmos that is darker, emptier, more isolated than the one we know. But they will also inherit the memory of what came before, the knowledge that once, for a brief moment in cosmic time, the universe blazed with the light of a trillion stars, and conscious beings arose to contemplate the beauty and mystery of it all. In this sense, we are not just observers of cosmic evolution, but participants in it. Through our observations and understanding, we become part of the universe's own journey towards self-awareness. Whether the stars will shine forever or gradually fade into darkness, the fact that they shine now and that we are here to see them represents one of the most remarkable achievements in the entire history of the cosmos. So when we look up at the night sky, we should remember that we are seeing not just distant suns, but the universe itself in one of its most magnificent moments. We are witnessing cosmic evolution in action, the ongoing story of matter and energy organizing itself into ever more complex and beautiful forms. And we are part of that story, perhaps the most important part, because we alone, among all the objects in the cosmos, have developed the ability to understand and appreciate the wonder of it all.